Good evening, everyone, and welcome to the Java Generics webinar with Raoul Gabriel Irma and Richard Warburton. My name is Adele, and I head up the community team here at eSynergy Solutions. We specialize in open source and cloud resourcing. If you are looking for a new opportunity, we can help you find the right role tailored to your skills and experience on either a contract or permanent basis. So please do send over your updated CV if you are looking for a new role. Should you be looking to build out your team, we can help you with hiring and attracting top talent. Alongside this, we can also help you with upskilling your employees around the latest open source and cloud technologies. Now moving on to some housekeeping. If you have any questions for Raoul or Richard, please fire them over via the questions box throughout, and they will answer your questions at the end of the talk. We are recording the session, and so the slides and recording will be made available and sent to you tomorrow by email, along with my contact details. So now I'm going to pass over to Richard, who will begin the session. Thank you.
Hello, everybody. How's it going? Are you good, Raoul?
I'm awesome. How are you doing, Richard?
Fantastic. Good to hear your voice. Good to hear your voice. So in this webinar, we're going to be talking about Java generics, and we're going to be going through the past, the present, and the future of generics. So we're going to talk about why they were introduced to begin with. Then we're going to talk about some of the features that are available in generics today, but which people rarely take advantage of. And then we're going to talk about what's happening to generics in, the Java 10 timeframe. So still 3 or 4 years away, but there's already quite a lot of information out there, which is quite interesting to know about how generics are changing and hopefully improving.
Richard,
but I think
generics,
yeah.
Isn't that something weird, question marks and symbols?
Yeah. So you often see generics, and they kind of look a bit like this. You have this situation where it's a very complicated type signature, a lot of question marks, extend, super, all that kind of thing. And I kind of get this, what this person here in the middle of the screen is kind of doing. Why have they put this here? What are those things doing? Why are they there to confuse us? And hopefully, the real takeaway of this talk is that when you see some of those more complicated features of generics, some of those more confusing things, that you won't have to be as confused and say, hey, why is that there? Why is that in the middle of the road? It'll be more clear as to what they're there for. Are you looking forward to it, Raoul?
Yeah, beautiful. And what's wrong with the road? I feel like it's a beautiful design here. It's fascinating.
Exactly. Okay. So let's first of all go back into the past to understand a little bit about how generics came about. You've got to take yourself back to good old 2004. It's a long time ago now, 11 years ago. And, Java, 20th anniversary this year, so it's an interesting point at which to take a historical look back. But we're not going to go all the way back 20 years, just 11 years. Back to the days when the Facebook was a new piece of software. Look at this stuff going on here. We've got some fantastic developer UI going on, these square brackets. What do you think about that?
Some binary numbers in the header, your core. And
very stylish.
For Greek friends in the audience, 2004 was when Greece won the Euro Cup.
That's true. That is true. And at the same time, generics get added to Java. So let's have a look. What were generics about, and what were they originally added to try and solve? Well, let's take a look at this very simple piece of code pre-generics. We've got a list, and we're assigning to it a new array list. I'm going to add some stuff in there, and we're going to loop over the list and print it out. So what happens if we try and run this code? Looks all right. When we run it, we find it prints out A, and then it prints out B, and then it has this nasty class cast exception. So our application here, even though it's very simple, has actually crashed. And if we look at where it's crashed here. Line 19, where we're casting it to a string. And the reason we can't cast it to a string is because we've added both strings and the number 1, which is not a string, into the application. And generics allow us to catch these kind of errors at compile time rather than runtime. So if I say, instead of it being a list that can contain any type of object, I say, hey, let's make it a list of string, then we immediately have a compile time error without actually running the program. So we've caught a bug before our program has ever been run. That's fantastic. As time went on, generics evolved, and the diamond operator was introduced in Java 7 to remove the additional need for generic type information. But a lot of the information that we're going to be talking about in this webinar are things which have been around in the generics days right from Java 5, so they're features which will naturally be available to you until we get to the future section of this talk.
So hold on, Richard, for a second here.
Yes.
If you could switch back to the code.
Yeah.
So just to address one question, we're going to try and mute each other so there's no echo. But why can't I just say list string? What if I just create a class that says list string, in one word? Why do I need to really care about those generics? Because I could achieve type safety by defining my own list string class and ensure that it only takes strings as an argument. What's wrong with that, Richard?
Right, that's an excellent point. You could have a class called a string list, and that's nice and safe as well. You'd have the exact same property that you can add a string to that string list, but not add any kind of int or any other value to it. But the problem with this string list approach is that you have lots of different classes and lots of different objects throughout your type system. So you might want a list of strings, you might want a list of numbers, you might want a list of users, all sorts of things. And you would have to duplicate that same boilerplate code every time round, which excellently brings us to the kind of trilemma that we're talking about here. Now, when we're talking about a trilemma, we're talking about specifically about the property of generics. We've got a trade-off between 3 different things. We've got simplicity, and simplicity means how easy is it for us to understand what the heck this code is actually doing. We've got static safety, and static safety is about trying to say these errors that might happen in our application, they get caught at compile time rather than runtime. And then there's concision, because we can have something that's nice and simple and statically safe, as you said, Raoul, but isn't very concise, requires us to repeat a lot of boilerplate time and time again to write our string list, our integer list, all the rest of it. And it's interesting because you can see languages fall into one of these 3 groups. We've got dynamically typed languages like Ruby, Python, or JavaScript, and they're both concise. You don't need to duplicate your list implementation every time for a different member type, and they're nice and simple. It's easy to see what's going on, but they're not in any way statically safe. Those errors propagate to runtime. We've got things that have generics or templates or whatever the name is in the language of choice, like Java, Scala, C#, C++, which combine both concision with static safety. And we also have other languages which require us to you have very restricted generics or simplified type of things. So Phantom is an example of a language that has very, very limited generic support. Cool. So we've hit our trilemma. And,
it's interesting to
Yes?
It's interesting to notice that actually dynamically typed languages, a lot of them are moving towards adding more static type checking, or at least at the type annotation level, which is
Yes, I think there's a proposal for doing that in Python at the moment, isn't there? And there's a number of things around doing kind of TypeScript, for example, with JavaScript, which is that kind of hybrid optionally typed language. So yeah, it's interesting to see people trying to get the best of both worlds, but they'll, as they add static safety, they'll lose their simplicity. You can never win on this kind of trade-off, I don't think. Cool. So let's have a little look at the present. So, Raoul, what's going on at present.
Okay, so the present is very interesting, Richard. So we're gonna review a few patterns that you can do with generics, including intersection types, the curiously recurring generics pattern. I just love this one, Richard. It's great for fancy dinners. And then wildcards, the scary question marks. So what we're going to do is sort of look at each of those patterns and see how generics can be applied in interesting ways.
Cool.
Okay, so section types. So we can't see you guys because it's a webinar, but raise your hand if you remember Venn diagrams at schools. Weren't they really, really awesome? You know, all those circles that were intersecting. And this is exactly what we're going to talk about. So an intersection comes from maths, and it says element that has to be members from both the set A and the set B. So if you guys could confirm that I'm not echoing anymore, and now that Richard is muted, just to check. So intersection coming from maths, we take intersection from two sets, and the middle bit is intersection. So it turns out in Java there's quite a similar idea, which is the intersection type. So if you look at this code here at the bottom of the slide, you know, we're simply saying T extends A. So that's a generic type here that says, well, T has to be a subtype of A. And if you remember in Java, you can be a subtype by either extending from a class. So let's say A was a class, then you're extending from it, you're a subtype of A. But you can also be a subtype by implementing an interface. So you get this sort of subtyping from both implementing and extending. Well, so we can extend this idea to saying T extends A and B. And that will create a sort of new sort of type that says that T is actually a subtype of both A and B at the same time. Okay. So let's see if we can do anything useful with this sort of idea. So let's look at some code. That's always the best way to look at some new concept. Here we go. Hopefully you can all see my fantastic hacker theme in IntelliJ. Richard prefers the white background, I prefer the black background. So let me walk you through this piece of code here. So essentially the requirement is we like to be able to read information from a source, from some input stream, and deserialize it. And what we get from deserializing this output is a person object. So let's look a little bit at the definition of the person. So person is this class here. You can see it's quite simply has a name and has a field for the age. Okay. So based on that, we can simply run this program. Let's see what happens. Great. So we're reading some information from some source, and we can see it's deserializing and finding name, Don Draper, age 89. But Richard, what could possibly happen here? What's typical in software development?
You're going to have some requirements.
Yeah, we're gonna have some requirement change. We all love requirement changes. So it turns out, you know, the boss is saying, well, fantastic, but I'd like to be able to read from some other format, let's say from a random access file. And this is a bit of a shame because we've got a sort of really pretty helper method here that actually just reads from the data input stream. You can see it's trying to open it, read from it, read the right information, the name and the age of the person, returning the new object. So we like to be able to use a random access file now. So what could we do? Well, let's uncomment this code here, which reads from a random access file. And you can see straight away the compiler is telling us, well, I'm really sorry, but I'm expecting data input stream and you want a random access file. That's a shame. Well, let's take our software engineering hat on, and you know, instead of duplicating this method here to accept random access file, maybe we can reuse the logic of this method. To do that, we're going to have to investigate a little bit more if there's sort of any common functionalities between data input stream and random access file. So let's take a look at data input stream. As you can see, data input stream is implementing this interface called data input. Okay. So if we look at the filter input stream, we can see it is an input stream, and it's also implementing closable. And this is made possible here because we've got this sort of nice try with resource from Java 7, which says the resource will be automatically closed. What about the random access file? Let's see how this is structured. Well, we can see that actually turns out this interface is also implementing, this class is also implementing the data input and the closable interface. So that's something random access file has in common with the data input stream. This is fantastic. So potentially we could merge those two interfaces together to provide a common ground for random access file and the data input stream. So, why don't we sort of create an interface here? So I'm going to create an interface that says data input closable, which extends both the data input interface, right, and is closable. So what I've done here is create a new type that says, well, I'm both a subtype of data input and closable, which is exactly what random access file is and what data input stream is as well. So, Richard, do you think we can use this interface to update our code so it can cope for those requirement changes?
I don't think so, Raoul. The problem here is that your random access class and your data input stream class are both part of the Java core library. So you can't say, take those classes which are in the core library and make them implement this new interface, right?
Precisely. Unfortunately, we don't have the master keys to the JDK. Brian Guts doesn't want to give them to us yet. We're working on this. But we can't modify the JDK code, so we can't just say random access file and data input stream are a subtype of this new interface. So we need to find a workaround. So what we can do using intersection types is to define a new type, as we were showing earlier. There's a subtype of a list of potential other types. So the way this works, we say in front of the root and type of a method, we're going to define this new type parameter here. I'm going to call it I. And we're going to say, well, I extends both from data input, but also from closable. So now I've got a sort of nice type parameter here, which I can use. So I now is sort of, if you will, is sort of magic type that says, well, I'm data input and closable at the same time. So I can use this as the argument type for source. Fantastic. I can use that inside my method body as well. Fantastic. So now our code is compiling. So if we run this again, we'll see that successfully we've managed to actually deserialize two person objects, even though they're coming from two different kinds of formats. So this is really fantastic. We've managed to introduce this type, intersection types to the rescue, to cope for the new requirement change. And we were doing this because we were unable to modify the JDK source. So, our recommendation is typically to introduce new names in the code base if they are useful for domain modeling. But in this case, intersection types were a valid example to introduce this new type. So Richard, what else can we do with intersection types? Is that the only use case for intersection?
Well, there's a couple of other uses inside the JDK as well, aren't there? If we have a look at, say, for example, this amazing example here, T extends object and comparable of question mark super T, T max, collection of question mark extends T col. This is one of those things where they've said, hey, people talking about generics need a complicated example to explain what's going on, and we're going to put it all in one method. But this is a genuine method in the Java core libraries. So, Raoul, what's going on here?
Yeah, that looks pretty scary. can I just say, Richard, you really need to fix your door because the handle here is definitely broken. So yeah, what is going on here? So let's take a quick look. So you can recognize the intersection, right? We've got this sort of the and symbol here. So we say t extends object and comparable. But you may be wondering, well, how can you have a comparable object? Surely it must be an object already. So what's the point of having object and comparable here? This is really silly. Why can't we just have this more simple signature here that says, well, I'm expecting some sort of t, and that's what I'm going to return. Well, we need to look back in the history a little bit on how how the Java libraries were designed previously. So before generics were introduced, so before 2004, this is the signature of the max method that you used to see in the Java API. So we've got a max method, which takes a collection. And we don't know what kind of collection it is. It's just a collection because we don't have generics at this stage. And the only thing that it can return is, well, an object, because the collection will contain object. And as you know, Java is compiled to bytecode, so it's very important to preserve binary compatibility in the future, which means the signature of the method is the signature that we're going to stuck with forever, unless we break binary compatibility. But there would be so many code bases out there potentially making use of this max method, which has the signature returning an object. So the problem we really have here is that max can only work if the elements inside the collections are comparable, right? If the elements are not comparable, there's no way for us to sort of find out how to compare the objects and find out which one is the maximum. So we could argue that actually this potentially was a design error that the library designers made in the past. So to overcome this problem, so if you can see in this slide, potentially they could have introduced generics in 2004 by saying, well, actually, I want some elements in the collections that are comparable. Don't worry about this sort of super stuff and these extend things. We're going to be looking at that in the other parts of the presentation. But this is one possible signature they could have come up with, which says, I've got a collection of comparable objects and I'm going to return something that is also comparable. Unfortunately, the way generics are implemented in Java is that they're erased, which means the generic information is lost at compilation time. So the only thing the compiler will generate is a signature that says, well, I've got a max method that takes a collection and returns a comparable object back. Unfortunately, this breaks binary compatibility because the signature of max is now different. So they had to come up with a trick to preserve binary compatibility. And the trick is actually to introduce this intersection type. So by saying object and comparable, what the compiler will generate is a signature that says, well, actually the first element in this section type is the type that makes it through. So in this case, we'd have the max method that takes a collection and returns an object, which is exactly the same signature that we had earlier, but now we get the benefit of having type safety using generics. So that's why we've got a sort of really complex signature. This is an interesting sort of example of how compatibility and a compatible evolution sometimes can introduce additional complexity in the language, in the libraries. So if you're using Java 8, and we hope you do, Java is really fantastic, you may actually see even more scary examples of intersection types and generics, which we'll cover in a second. But you can see in this slide here, I've got another intersection type that says, well, what we return is a lambda expression that matches a comparator, but it is also serializable. Potentially, you've got a comparator as passed to a tree that you'd like to sort, so the comparator object still needs to be serializable. So this is also a trick here. So the compiler, well, my lambda expression here that returns a comparator object has to be serializable. So that's another scenario where you may see intersection types. Okay, so I think we've covered intersection types, and I'm going to pass over to Richard that will talk to us about this. What is this extends in stuff, Richard?
Yeah, that's a great question. We have this kind of curiously reoccurring template pattern, don't we, with generics? So we see things like a class of enum, e extends enum of e, where in the generic type, it's referring back to itself and referring back. And when you look at it initially, it does look a bit weird, doesn't it? It looks a bit like this door. You know, things are off to the side slightly. It's a bit confusing. What's going on there? But fortunately, we have a well-known internet meme that describes what's going on here, right?
Are you gonna bring up the dog meme?
I am going to bring up. Can you switch the presenter over to be me, by the way, Raoul?
Sure. That's a good idea. So let me change presenter over to you, Richard.
Thank you very much. Perfect. Yes. So there's the Yo-Dog meme, which crops up in this situation, and really the Yo-Dog meme was there entirely to describe this curiously recurring generics pattern. I put a type parameter in your type parameter, so you could do what exactly? Well, let's have a look at some code. My code here is going to be a couple of confused people. We've got a class called ConfusedPerson1 and a class called ConfusedPerson2. And ConfusedPerson1 is called John, and ConfusedPerson2 is called Bob. So, why are John and Bob confused? Well, ConfusedPerson1 and ConfusedPerson2 both implement this interface called clonable. And the clonable interface has a generic type T, so it's kind of saying, hey, I'm clonable, and the clone method returns T, which is the type of the clone. So if we go back to that example, and when you call clone on yourself, you'd expect to return an object that's of the same type. So we should be able to say ConfusedPerson1 equals ConfusedPerson1.clone, but that doesn't work with John. You can't clone him and get a ConfusedPerson1. ConfusedPerson2, Bob, well, you know, can we do that with ConfusedPerson2? Yeah, that looks good, doesn't it? So it looks like Bob isn't confused superficially. But if we go a bit further, we can find this double clone method. And this double clone method takes a person, then clones them, and then clones them again. Now, that works if we're just doing ConfusedPerson2, but actually, we could write this generically, couldn't we? We could say clonable of question mark, because if you can clone something, that should return you the same type, and then it should be clonable again. But that doesn't work here, so ConfusedPerson2 can be passed to the double clone method, because ConfusedPerson2 implements the clonable interface, but you can't clone the person and then clone them again, even with this wildcard. So what's going on here? In order to see what's going wrong, we need to have a look at the declarations of ConfusedPerson1 and 2. So ConfusedPerson1 implements clonable of string. That's not right. If you clone a confused person, you should get a confused person back out again. So we need to change this generic type to be ConfusedPerson1. And we need to change the clone method to return a new confused person with the same name. Okay, that's good. So if we do that, we can go back to the main method and we can see that compiles. But actually, it was a bit of an error to let ConfusedPerson1 be clonable of string to begin with. So if we go back to the clonable interface, we can force someone to clone something and then only return something that's clonable using the curiously recurring generics pattern. So we can say clonable of T extends clonable of T. It returns something that's clonable and then gives you back the thing that you can clone again. And what this means is that if our clonable person of 1 tries to return string, we get a compile error immediately because you can't say clonable of string because string isn't clonable of string. Only ConfusedPerson1 is clonal or confused person 1. And it also means by making that recurring type parameter in the template, in the interface declaration for our clonable interface, that we can call clone twice. And now, if we run this code, oops, sorry, I still had the error from the first guy again. So if we run this code, we can see that it prints out John, where we've cloned John and printed him out, and then it prints out Bob, where we've cloned Bob and then cloned him again. Perfect. There we go. We're able to both solve a compile error that we previously had and also abstract over a type using the curiously recurring generics pattern. And now I'm going to pass you back to Raoul to talk about wildcards, which are where we see these question marks all over the place.
Fantastic. So I think that was a great example of how a generic feature can add additional type safety in the program. So what we're going to be looking at now are wildcards. Don't we all love those question marks, super question mark extents? What do they actually mean? Well, it turns out it has a lot to do with subtyping to get additional flexibility when we design a library. So we may want a library to be able to cope for different kinds of types. That's the sort of situation where wildcards are useful. So just to refresh a little bit about subtyping, we're going to get started with a simple domain. So in this code, we've got messages. Messages is simple wrapper around a message field. And what we're going to do is to define two subtypes of a message. So we can have email message, and we can also have text message. So if I look at text message, you can see it extends the message class. And same thing for email message. So let's do some subtyping 101. So we've got a message here. Then we can say, hi from Cambridge. So I can assign an email message object to a message variable because email message is a subtype. So this also means if I've got a log method here that accepts a message, then I can pass on the message directly. Or I could say, well, actually, you know what, I want a text message. So this is standard subtyping that we all used to. What about arrays? Well, let's say we have a message array. And what we're going to say is, well, I like one email message that says, hello, everyone. Okay. So we've got an array here with one element. And what we're going to do is to log each of the message inside that array. So I can say log all that takes my messages. So let's run this code so far just to see what happens. So yeah, that's great. The first line is coming from here, and the second line is coming from this guy. Cool. Well, let's see if we can actually have some fun with this. So what I'm going to do is to say, well, why don't we have, and I'm going to make it a little bit more explicit in this case, but let's say we've got an array of email messages. Okay. So just going to use this guy here. So that's good. And it turns out actually subtyping works also with arrays. So I can say message messages equals emails. And this works because a email message array is also a subtype of a message array. So this weird symbol that I'm using here means subtyping. So it's like saying email message is a subtype of message. Then we've got an array of email message, a subtype of an array of message. Okay, so that's quite useful. But what happens in the situation where, you know, someone else is using your data here, your array of messages, and saying, well, you know what, I really like to change the first element to not an email this time, but to a text message. So we could say something like text message, hi again. Okay, and this is allowed because my message here is actually an array of message. Let's run this code and see what happens. Looks like we've got some form of exception here, which says Java lang array store exception at lines 39, which is exactly where we did the assignment. And why could that be the case? Well, it turns out actually the only array that we've got on the heap is the email message. We're just saying, actually, we want a different view to this email message by assigning that to a message array. So the question is, when we say emails 0, what do we get back? We should get a text message back. But unfortunately, here we're defining that the array emails is an array of email message. So this is really confusing, isn't it? Because somehow we've managed to break the type system. And that's one of the issues with arrays in Java. They're flexible in the sense that you get this sort of nice subtyping property. But unfortunately, they're not type safe because you can sort of exploit this flow here. And there was a very good reason for why this was allowed in the Java API. You know, before generics, let's say you want a sort method that takes an array of objects, then you need to be able to pass an array of integers, you need to be able to pass an array of any kind of objects that you want, so you can reuse the same sort implementation. So that's the reason why arrays were implemented in this way. So let's now look at list. Our generics implemented differently. So it turns out I've got another method I call logall that's just going to log a list of messages. So which means, let's say I've got logall here. Let's see if we've got some pre-made list here. Yeah, so I've got a message variable here. So let me uncomment this logall here. All right, so we're just going to pass a list of messages. Let's run this. Let's uncomment this this array store exception. Yeah, fantastic. So logall works. We passed a list of messages, and as expected, this does the trick. So let me also uncomment all those other guys so we don't get confused. Fantastic. Well, so what happens if now instead of passing a list of messages, I pass a list of email messages? So explicitly a list that contains only email message. Well, it looks like this doesn't work. It says cannot resolve the method. So this is a compile error. With arrays, this would work. With list, this doesn't work. The reason why this doesn't work is because we say generics are invariant, which means a list of email message is not a subtype of a list of message. And the reason for this is that we actually get type safety. We can't exploit the same issue that we had with arrays. Unfortunately, we traded type safety for flexibility. You know, it's kind of silly. Actually, I've got one method that can deal with list of messages. Why can't it deal with list of email messages, a list of text messages? We'd like to get this flexibility. Well, don't you worry, we've got wildcards to the rescue. So wildcards is quite simply a way to extend subtyping for generics. So what we like to do is to say, well, my local message here is going to be able to take a list of anything that is a subtype of message. And the way to do this is to using this, I can admit, sort of weird syntax. So question mark extend message. What that says is actually, I want a list of anything that extend a message. And you can see here that actually our code here now is actually compiling. So if we run this, we can see, fantastic. We actually printing the emails. So let me comment that line off as well so we can see that actually we're only talking about emails. Fantastic. But what's interesting is if we go back in this body, here this method, now if I say message dot add, you can see we sort of get this weird signature here, and that's going to prevent us from adding elements in this list that are not email messages. So we get a sort of read-only view, but we can't write to it. So we still get type safety, something we didn't get with arrays. So that's useful. So we get flexibility now at the API level, which is fantastic. So let's sort of look at the little brother of the question mark extents. We'd like to look at question mark super, which is, I admit, really weird. So the scenario is we're able to log messages, but we like to be able to log messages in a specific way. At the moment, the only thing we're doing is printing the message, but maybe we like to be able to customize the way we can log the message. So there is a new interface introduced in Java 8 called a consumer. So for now, we're going to say I want a consumer of object consumer. What a consumer says is simply, well, I can accept some object of the type T, and we're going to return void. So that means we can work with that object, we can print it, we can log to a file, we can do a bunch of stuff, but we return void. So instead of printing the message, what we can say is, well, consumer.accept the message. And now all we need to do is to provide different implementation of consumer that will say how we'll log the object. So what I'm going to do is to create a consumer of object that says, well, I'm simply going to print out this object. Okay. So here I'm using the method reference feature in Java 8. So I'm able to extract this method, store into an object, and now we can say log all. So this one here doesn't compile anymore because log all is expecting 2 arguments instead of 1. So we'll comment it out. So we've got log all. We say, well, I want my list of emails, and I want to print them. So let's just run to see if this works as expected. Fantastic. But let's say now, we want to a more customized way to be able to deal with the messages. So let's say I want a consumer of message, which instead of printing the object using the toString method is actually only going to extract a specific field. So in this case, we're going to say just print the message. Okay. So here I'm using a lambda expression for this. Again, it's a Java 8 feature. And we're going to pass print message. This doesn't work. This says we can't apply the consumer message to the consumer of object. Well, because the method logall expects a consumer of object, and what we're passing to it is a consumer of message. But that's a bit silly, isn't it? Surely, if we're able to consume from a message, then the more general version, which has less information, we only know it's an object, should work too. So the trick here is to use question mark super. So let me say question mark super message. What that says is I'm going to accept a consumer of a message or anything else that is a super type of message. An object is a super type of a message. So now our code is compiling, and let's just run this to see behavior, and says hello by email. So we've only actually printed the message itself. It's filled. So this is fantastic, and I can pass on print as well, which is a consumer of object. And let's run this code again. Fantastic. So with wildcards, we've managed to extend the subtyping principle, both by saying a list of anything that extends a type or message. Also, we've got the sort of alternative which says, well, we'd like to have anything as a super type of a given type, in this case, message. And the reason for using these features is actually be able to have an API that is more flexible. My local method now can take text messages, email messages, or list of messages, but also can take consumer of different kinds. So that's the benefit of using wildcards. We get flexibility, but also type safety for generics. Okay, so let's go back to the presentation and talk a little bit more about question mark super, because question mark super is one of those wildcards that you often see, and it's a bit confusing. So it turns out with Java 8, question mark super is becoming really popular with functional interfaces. So if you look at a comparator, the comparator interface actually defines a method that says, well, I want to be able to compare two objects. So surely if you're able to compare two emails, well, you should be able to compare two messages, because messages has less information than the email has. So that's a use case for using question mark super for the comparator. And it turns out a comparator interface can only be used with question mark super. And you'll often hear the sort of really scary academic terminology, contravariance. So we say that the comparator interface can only be used contravariantly. What that means is that you can only use it in the context with a question mark super, so expecting a super type. And this is the same story with predicate, which is another interface that was introduced in Java 8. So predicate says, well, I want to be able to test out some object given an argument and return a Boolean. So for example, checking if a message is of a given length. And that's the same story. The predicate contains only one single abstract method called test, which only can be used contravariantly. The type parameter t here appears as an argument. So if type parameter only appears as an argument, that's when the interface can be used contravariantly. So you'll see question mark super sprinkled all over the place in the Java 8 API. So often with those features, it's sort of interesting to look at how they're used in practice. And there is research that is looking at the use of generics in Java. Here's the paper if you're interested to read more about it. Essentially, what they found is by looking at millions and millions of lines of code, is they found actually 90% of the generic use are simply with collections. List of string, array list of string, hash map string of string, and set string are 90% use of the generics in Java, which is, I think this is mind-blowing, right? Because all those complex features that we see are actually not used very much in practice. You will often see them only in complex libraries, such as the collection API. So I encourage to read this paper if you're interested in this topic. Okay, so we've covered the present. So we looked at 3 interesting use of generics: intersection types, the cursory recurrent generics pattern, and wildcards. Now what we're going to look at is the future. Where is Java heading? And are generics going to get easier? Or going to get more complex, more sophisticated? Lots of questions. So yeah, Richard, do you remember this movie?
It's time to go back to the future at 88 miles an hour, right?
Precisely. So I love the look on his face. I'm scared. So let's, the first feature we're going to look at is use-side variance. So it turns out wildcards provide a lot of flexibility, but you have to use them in your application code. They're sort of enforced in your libraries. You say, well, I want this message to be used covariantly or contravariantly. So that's an explicit decision that you make as a user rather than as a library designers. So we call this use-side variance. That's what wildcards are. You sort of decide how you want your type to be used, covariantly or contravariantly. And you can get both if you want to, just like in this example with message. The alternative is called declaration side variance, which is popular in other programming languages, such as Scala and C#. And the way it works is at the library level, you specify how the type parameter should be used. So in this case, we can say consumer can only be used contravariantly. So when you use the consumer interface, you don't have to say that it's consumer question mark super message anymore. The compiler knows because consumer at the library level was declared to be contravariant. And it's a similar story with covariance, so with question mark extents. In this case, we want to say, well, the stream interface can only be used covariantly. So when you use it at the library level, you don't have to say question mark extend message anymore. So it's one way to avoid, to reduce verbosity that you can often see with wildcards. So that's declaration side variance. And it turns out there's a proposal actually for Java to implement declaration side variance. And that's a way to reduce verbosity in the code, but also still get the flexibility of subtyping for generics. There are downsides with both approaches. So use type variance is more flexible because you can say type can be used covariantly and contravariantly. You can pick. You can have both if you want to, but it adds a lot of verbosity and annotations in the code base. Declaration side variance is really neat because it pushes down the complexity of the variance annotations at the library level. So as users, we don't have to worry about it anymore. We don't see it. So this is fantastic. We don't see sort of clutter in the code. Unfortunately, this means that the decision of whether a type can be used covariantly or contravariantly has to be done explicitly at library level. So you can't have both. So often that means, for example, in case of list, you need to split the list in the read-only part of the list that's going to be used covariantly and the write-only part of the list that's going to be used contravariantly. So you can get this more complex type hierarchy. But that's what C# and Scala have adopted, and that's what Java hopefully will be adopting as well. And it makes a lot of sense in the context of functional interfaces because they can only be used in either a covariant way or contravariant way. So really looking forward to see this happening in Java. Okay, so I'm now going to pass over to Richard that's going to talk about actually additional features that are going to make it into Java 10.
Thanks. Yeah, so I'm going to be talking a little bit here about value types. And the idea with value types are that they code like a class and work like an int. That's the kind of mantra that people are going with value types. And the idea there is that there is no identity to a value type. So you know if you've got a normal object, you've got kind of a heap object that's sitting there somewhere and there's a reference to it in the heap. And you've got, you know, the concept of identity-based equality. Is that the same exact object? And value-based equality, which is, you know, are the actual values the same? And value types try and unify the two. So there's no concept of an independent identity. It's just a struct of values. Okay? Raoul, is there any chance you can switch over presentation control to me? Thanks. Cool. And the motivation for doing that, for introducing that value-based semantics is twofold. Firstly, you have compactness. Now, every object in memory needs to have a couple of things in its header at the top of the object which store information about the object. And the first one of those is what's known as a mark word. And the reason why you have a mark word there, well, there's several reasons, but one of the things which mark words do is they have lock information. So every time you use the built-in Java locks, like kind of the synchronized keyword, it means you can use an object as a lock, and the information about where the lock is, what its thread it's biased to, things like that is in the mark word, as is potentially some GC information. And there's also what's known as the class pointer. So that's a pointer to a class in the implementation called class, which refers to what type of Java class you have. And depending upon your architecture and VM, these kind of header things end up eating 8 to 16 bytes per object. Now 16 bytes on a 64-bit JVM with no compressed oops doesn't sound like a lot of memory, but you've got to bear in mind it's per object. So if you think about the object integer versus the primitive int, the primitive int is taking up 4 bytes, but the integer object is taking up 16 bytes for the header plus 4 bytes, and they get aligned to be on a multiple of 8 bytes with regular objects. So it's going to take up 24 bytes to hold up 4 bytes worth of information. So it's 6 times more memory than it really needs. And if you've got an array of 1,000 or 10,000 integer objects, you're wasting a lot of memory over just having those as int objects. So this is one of the benefits we get. The other benefit has its, technical fancy CS name as sequential locality. What I like to think of it as is flatness. Now, over time, modern CPUs have evolved and gotten faster and faster and faster. But your memory, on the other hand, has been getting faster still, but at a much slower rate. So while CPU core count, transistor counts double every 18 months, the transistor count still does. Memory speed has only been going up at an average rate of 9% a year for the last decade. And more and more these days, there's a great deal of importance placed upon your CPU cache, how much locality you're getting out of your CPU cache. And what that means is how good is your code at letting your CPU cache predict what data you need to next load into its CPU, and consequently reduce the overhead by prefetching that data. Now, if you lay out your data sequentially in memory, as this kind of thing is on the left, so we've got like a list of users and the user has an ID and a name. And in the example on the left, we've laid them out sequentially in memory. And what that means is whenever you read the user object or the user value type, the ID and the name, you're sequentially moving through memory, and your CPU cache can prefetch that data. It can say, they're going sequentially in memory. It's the next thing. I'll start prefetching the next thing in. I'll just stream it in nice and efficiently. In the case of the stuff on the right-hand side, we've got a regular list of objects, and there's a pointer to a user and a pointer to the ID and a pointer to the name. So every time you want those pieces of information, your CPU has to go pointer chasing to some other random offset in memory, which could be arbitrarily moved by your garbage collector. So moving from this kind of randomized layout to a more sequentially flat layout is going to massively improve the speed. In fact, you're talking in some cases 10 or 100-fold speed improvements from referencing memory that's sequential versus randomly aligned. But there are downsides to the introduction of these value types, and the downsides primarily come in terms of more complexity in generics. So things like value types, because as I said, there's no header, there's no mark word, there's no way of doing reference-based identity checks, or reference equality, checking two objects of the same object, or locking on them, or doing condition variables, so calling wait and notify on the object. You just don't get that. So you need to add a concept to generics in order to let it say, here's going to be a generic type, but what you do with it is restricted. You might not be able to do reference equality checks. You might not be able to use the synchronized keyword or call wait and notify. And the concept being added is the idea of Annafication. So in Java 10, I mean, this might not be the syntax, but this is definitely the direction things are going in conceptually. You can say, well, you will be able to say, hopefully, class array list of any t implements list of t. And what this means is your array list will take any type, a reference type or a primitive type or a value type as its parameter. And what you're committing there, the contract you're making with the compiler is saying, I'm not going to do any reference equality or locking or condition variables because that will cause a compile error. So that's Annafication. And what that buys us is the ability to do primitive specialization and value type specialization. So you'll be able to say a list of int numbers is new array list, and that'll be a genuine list of primitive int values rather than boxed integer objects, adding the numbers in, and they'll all be sequentially laid out in memory, so that'll be nice and fast. If you want to read about this in more detail, there's a state of the specialization paper out there by Brian Getz et al. And there is also a project called Valhalla in the OpenJDK project, and there's a mailing list for Project Valhalla which talks into more details, because this document's a little bit out of date now. There's more discussion on the mailing list as well. So if you want more information, you can go there. Cool. And I thought I'd just kind of summarize by talking about a few of the other little bits and bobs we have in terms of generics and type systems. So, you know, there's things like unbounded wildcards, which are where we have just a question mark on their own. And we've talked about type bounds, so with just the extends keywords. Erasure itself is one of those things in generics which has advantages and disadvantages. So Java's implementation erases type information away at runtime, which does result in some downsides. It makes it harder to do these things like these primitives. So erasure is not going away. That is still going to be there and still has its backwards compatibility advantage, but there will be some specialization for things like primitives and value types where those specific instances of array list will not be erased. Obviously, generics doesn't solve all our static safety problems. Java still has a load of problems where, we have errors cropping into runtime from compile time, and hopefully more type system features can improve that situation in the future. And if you're interested in general in looking more about those kind of language features, then there's this concept called a lambda cube, which I'm not going to go into detail in this talk about, but if you want to Google around, the lambda cube talks about the relationship between different type system features. And if you want any of the source code from this talk, it's at that link below. So we just conclude and summarize what Raoul and I have talked about today. Over time, you see the kind of usage patterns of the language change as new features are added. So a great example of that was bounded wildcards weren't very commonly used until Java 8, but now with Java 8, they're used quite a lot. Things like consumer and supplier are things which you really need those wildcard features. And as a consequence, you see the usage of generics growing in scale and complexity. To begin with, it was just collections. Now there is a lot of Lambda-related code, collector code, data processing pipelines, which are generic. But even though the complexity is growing, a lot of that complexity burden is still on library authors, which is fantastic. I love it when people at Oracle do work so I don't have to. That's great. Or even people outside of Oracle, library authors in general. And that's a good way to go. And hopefully, if Java down the line gets declaration site variants, even more of that complexity burden can be pushed to library authors. But most importantly, just to recap and go back to our original trilemma at the head of this talk, the static type safety ends up giving us this kind of trade-off between simplicity and flexibility. We get the safety, but we lose a bit of simplicity or a bit of flexibility, and there's no clear-cut win. Okay? I'm going to give you guys the opportunity to ask some questions. You can ask questions through the GoToWebinar system, and Adele will forward them onto us. Just to recap a few other bits and bobs, both Raoul and I are Java book authors. Raoul wrote Java 8 in Action with Manning on the left, and I wrote Java 8 Lambdas with O'Reilly on the right. And we provide training courses on Java 8 through iteratorlearning.com. So go there if you're interested in going more in depth on Java 8. I'm also a Pluralsight course author, so if you go to that link at the top, you can see some courses I've put on Pluralsight for improving your ability to test code with Java, and also a new course now on generic. So if you want something that goes into a lot more detail and at a much slower pace, or maybe team members might be interested in that, that's one to check out and take a look at. Raoul also runs the Cambridge Coding Academy, which is both providing things like machine learning courses to day-to-day Java developers and day-to-day professional software engineers, and also, very importantly, teaching the next generation of kids how to code. So fantastic stuff, Raoul. I'm just going to hand you over to any questions. Just a quick question to Adele. Has anyone asked any questions? Has anyone got any open things they'd like to know about?
So I have forwarded it over to you, Richard, so have a look on the chat box. You can see a few questions there.
I can't see anything since all good now. Can you, Raoul, can you see the questions?
I can't see anything. All good now.
So there was one question around sharing the source code. from the examples that you've been explaining?
Okay, so if we just go back here, there's a link at the bottom of this slide. So we'll put the slides on SlideShare, and we'll give a link to Adele so she can email out attendees.
Great.
And here there's also a link in the slides to the source code examples on GitHub here. So that's fantastic. So if you're looking for the source code, you can look at it there. I see a question. How does value types affect garbage collection? Great question. Well, value types affect garbage collection in a couple of ways. If I can just pop back to this slide here. If you've got an array allocated on heap that has a bunch of objects coming off, there's garbage collection cost in terms of tracing all those objects. So that's finding out whether they're really alive or dead and need to be garbage collected. So that gets reduced quite significantly by putting things sequentially located, because the value types don't require you to go off and trace all these objects. You can just trace the big array. But the even bigger win for value types is that value types are naturally stack allocated objects. So if you've just got a local variable that's a value type, that'll be allocated on stack and will die at the end of your method scope naturally. So that's one of those situations where it's totally changed the GC mindset cost by stack allocating, and that significantly, it doesn't change the GC cost as much as it means there's no GC work required at all for those stack allocated objects. Cool. Okay. Thanks, Patrick. Good. Cool. Did you have anything to add to that, Raoul?
You did a great job.
Okay. Murray asks, about sequential locality, are we moving away from pointers? I think that's the thing in general that, yes, we should be looking at moving away from pointers wherever possible and trying to think in terms of sequentially or predictably allocated data behavior. So there's already some things you can do even without value types that benefit this. So at the end of the day, array lists and linked lists, if you're iterating over them, you'll find that array lists are nearly always quicker because the array of pointers has been sequentially allocated, but if you've got a linked list, they get kind of randomly allocated, even the linked nodes, so they end up being faster as an array list. And in fact, if you have a look around on the internet, there's a talk I've given called caching in, understand, measure, and tune your CPU's cache behavior, and that goes into all sorts of detail about CPU caching. And it's basically me talking about this topic for an hour. So if you're interested in that, you might want to have a look at that in terms of more details. But yeah, I think we're really kind of moving away from them as we're moving forward. Cool. Thank you for asking the question, Murray. That's great. Okay, cool. I guess that's it on the questions front. Do you have anything else to say on the wrap up front, Raoul, before we head off, or Adele?
Hi, yes.
Yeah, feel free to add the questions later on, but I think Adele will have the video and the slides.
Yes, the recording and presentation will be made available online, so everyone will get an email copy sent over to them with the link to the recording tomorrow.
Thanks a lot.
Great.
Yeah.
Thank you, everyone.
Bye.